Hello everyone. For this week's lab, we'll be discussing about acceleration measurements. Acceleration is measured using accelerometers. Accelerometers are used to measure position, velocity, accelerations of a body. So, if some of the applications are they are for example they are used in your mobile phones to detect the number of steps you are taking. Uh, they are also combined with other sensors such as gyroscopes and magnetometers to detect the orientation of a body in the world coordinates. So you can it's basically used to uh, get motion capture data, uh, and also it's used in aeroplanes, ships to find how uh, fast they are going, their acceleration, and like they have a lot of other applications too. So today we'll be looking at how these accelerometers work, and we'll be using the accelerometer to find the natural frequencies of flexible beam. So accelerations are divided into two types. One is impact, and other one is vibration. Impact is a large acceleration that is applied in a short amount of time, and vibrations are small repeated accelerations over a long period of time. So we'll be looking at two accelerometers. Uh, One is seismic accelerometer, and the other one is piezoelectric accelerometer. So the basic principle behind the accelerometers is the moment of inertia. So the acceleration is found using the inertia of a small object inside the accelerometer. So if you look at this diagram, you can see, so this is the seismic accelerometer. So they have a small mass which is inside the uh, accelerometer, and it is connected using a spring and a dashpot. Uh, so when the object moves, when this object moves, the mass moves in the other direction due to inertia, and when the mass moves, the position of the mass is recorded on the position sensor. So the position sensor can be anything, as you saw in the previous labs. It can be potentiometer, uh, uh, it can be encoders, it can be uh, any other linear motion detectors. So uh, you can use those to find how the mass is moving, and based on that you can figure out how much the how much speed at the speed at which the object is moving, right? So that's the basic principle on how seismic accelerometer works. So uh, but the problem with seismic accelerometer is that it works well with low frequency accelerations, but when it comes to impacts or high frequencies, it doesn't give an accurate result. So to counter this, we use piezoelectric accelerometers. So here for the piezoelectric accelerometer, instead of spring and a position sensor, will be using a piezoelectric crystal. So the piezoelectric crystal is nothing but a material which generates charge when force is applied on it. So if you squeeze the crystal, it will generate a charge which is directly proportional to the amount of displacement you do on the crystal. So principle behind piezoelectric accelerometer is similar to the seismic accelerometer. Uh, so when the object moves, the mass moves in the other direction due to inertia, and it squeezes the piezoelectric crystal, and based on how much it squeezes the crystal, the amount of charge can be detected, and using that charge you can find out how much displacement occurred. So using that displacement you can figure out how much was the acceleration, uh, was the acceleration at which acceleration of that moving object, right? So this is the basic principle behind accelerometers. So accelerometers usually are they move in one direction, and they are not affected by other directions. So here this moves in one direction and it's not affected in this direction or in the z direction. But nowadays, so that's called one axis accelerometer. So if it doesn't get if it doesn't get affected from any other directions, and it only works in one direction, it's called one axis accelerometer. Nowadays we can get three axis accelerometers, so it can detect the acceleration in three axes. So, so for this lab, we'll be using the accelerometer to figure out the natural frequency of a flexible beam. So what we'll be doing is we'll be taking a cantilever beam, we'll be attaching the accelerometer directly to the beam. Uh, the accelerometer moves at the same speed as the beam, and we'll also attach a shaker, and uh, so the accelerometer's input, so, sorry, the accelerometer's output would be given to the an amplifier to amplify the output, and we'll be reading that through the dashboard, uh, and we'll also be uh, powering the shaker using the signal generator to give it specific frequencies at which we can move the beam, right? So, uh, the way we find the natural frequencies of the beam is by finding the position and the frequencies at which resonance occurs. So resonance is nothing but if you give a constant so if you apply a force at a frequency which is equal to the natural frequency of an object, the constructive interference happens, and the amplitude increases and it starts to vibrate rapidly. So what I mean basically is so there are two kinds of interference. One is destructive interference and one is constructive interference. So, for example, like if you have two waves uh, which are opposite to each other, destructive interference happens, and the output would be, as you can see, like the output would be all almost a straight line, and in the case of constructive interference, the opposite happens. When two similar waves interact with each other, constructive interference happens, and the amplitudes add up, and the resulting wave would be double the frequency of the initial waves, right? So that's how we'll be figuring out the natural frequency of the beam. So uh, we'll be increasing the frequency of using the shaker. So in the beginning we'll be starting at frequency of 1 hertz, and we'll slowly move increasing it by 1 hertz. So we can see at which frequency the resonance happens. So uh, for example, like when the frequency happens, we know the amplitude increases. So in the experiment you can see that the amplitude increases as we increase the frequency. And the way we can figure out which natural frequency the resonance is happening at is by counting the number of nodes. So for first natural frequency, there is only one node. A node is a stable point where which does a stable point where the movement is minimal. So here the red mark is a node. So you have one node, so it's the first natural frequency. In this case you have two nodes, so this is your second natural frequency. And in this case you have three nodes, so it's the third natural frequency, right? So this is how you can figure out how to find the natural frequency using an experimental procedure. Uh, but if you want to find out how to find the natural frequency in a theoretical way, what you can do is so there are two easy methods to find out the natural frequency using the data. So uh, if you take the cantilever beam, and if this is your beam, and if you apply pressure on the far end, it starts to vibrate. And when you move the beam, you can see in the experiment that you will get a graph which would look something similar to this. So there would be a wave with decreasing amplitude, and so this is called a damping wave because it dampens with time. So using this, we can figure out the first natural frequency of the beam. So uh, the time between the first amplitude and the second amplitude is your T1, and using this T1 you can get the first natural frequency, which is nothing but 2 pi by T1. And you can also find the damping ratio using this equation, where A is your amplitude, so you can take any two amplitudes, so you can take A1 and A2. So this would be your A1 and this would be your A2. And using this you can find, after you solve everything, you can find the damping ratio. So this is how you can find the first natural frequency and damping ratio using the the plot. And the second method is by using this formula, which is beta I and under root ei by ml cube. So here E is your Young's modulus, I is your moment of inertia, m is the mass of the beam, L is the length of the beam, and beta is it's a coefficient which is unique to different materials. So here for our case, we have the beta 1, beta 2, and beta 3. Uh, Beta 1 is for first natural frequency, beta 2 is for second natural frequency, and beta 3 is for third natural frequency. And and for the mass, we have the density of the beam, so we can use the density. And so we know that density is equal to mass by volume. So which is also equal to mass by area into length. So we have the area. So from the given data, we know we have the area, we have the length, so we can get the mass. And using the we have the mass, we have the length, we have the moment of inertia, we have the Young's modulus, and we have the uh, coefficient. So using this, we can find out the first, second, and third natural frequencies. Okay, so that's how you can find the natural frequency using experimental and theoretical methods. Okay, so I hope you guys had fun with if you have any questions, email me or meet me in office as through Zoom.